Hi everyone, welcome back to chemistry. In this video, we're actually starting our second study guide, which is all about atoms, elements, and matter. And we're going to start with Roman numeral 4 on your study guide, which is classification of matter. So we already talked about section 3.3, which is temperature, and 3.4, which is energy, in the last week or the last module. So we won't go over those again, but we will do section 3.1 and 3.2 in this video, and then we'll start 3.7 in the next. Okay, so matter. So matter, again, remember that matter is defined as anything that has mass and takes up space, okay? And matter is classified according to its composition. In other words, according to what it is made of. Okay, and there are two types of matter. There are pure substances, which have a fixed or definite composition, and we'll talk about what that means. And then there's mixtures, which contain two or more different substances that are physically mixed, but not chemically combined. And we'll talk about what that means as well. For now, just think of it as there are two different types of matter. There's pure substances, and then there's mixtures. So let's go in depth. Pure substances. So a pure substance is, again, a type of matter with a fixed or definite composition. So an unchanging composition, right? And that pure substances are actually broken down into a further two categories, which is elements and compounds. And I'll show you an infographic in a little bit that kind of breaks this down really well in like a summary. But for now, a pure substance is broken down further into elements or compounds. So an element, you might be familiar with the term element. If you've ever looked at a periodic table, you might have kind of run into it there, or you just in your everyday life, there's all kinds of elements that you come into contact with. One of the examples that books gives is this aluminum can. So an aluminum can actually consists of tons and tons of atoms of aluminum, or aluminum atoms. And aluminum is an element on the periodic table. It's abbreviated AL, capital A, lowercase l. We'll talk about those more in the future, elements. But other ones you might be familiar with are like hydrogen or oxygen or chlorine in swimming pools. Iodine is added to our salt sometimes. What else? Silver, zinc, copper, nickel, aluminum, like I said. So those are all elements. So something, a pure substance can be either elements like that, where they're just composed of one type of atom, like that aluminum can, or compounds, which are composed of two or more elements, but they're always combined in the same proportion. So what does that mean? So something like water would be a compound, right? There is, actually, I think this slide goes into it more. Yeah, let's save this a little, table this for a second. So elements are pure substances that contain only one type of material, like I said. So some examples there for you. Copper pennies are actually really interesting. In the past, they used to be made with completely just of copper atoms. Nowadays, they're kind of a mixture, but we'll go into that later. So copper would be, an element. Lead is an element you might be familiar with. It's actually abbreviated PB, which is kind of weird. And then aluminum is an element, right? Okay, and then compounds. So this is what I wanted to get to. So the compounds, remember, contain two or more elements, but they're elements that are combined in a fixed or definite ratio. Okay, so that ratio is unchanging. If you change the ratio, you're changing what you have. So for instance, looking at these two here, we have hydrogen peroxide and water. Notice that the only difference between these two things is that you have one water here, right? When there's nothing represented there, we just assume there's an imaginary one. And then did I say one water? I meant one oxygen atom. And then here you've got two here, so two oxygen atoms. So this 2 is going to the H before it, and that 2 on the O is for the O. So 2 hydrogen atoms per every 2 oxygen atoms versus 2 hydrogen atoms per every 1 oxygen atom. Okay, the big difference here is even though there's only that tiny little change, right, 2 versus 1, we drink water all the time. I really don't recommend drinking hydrogen peroxide, right? Hydrogen peroxide you can put on minor wounds, stuff like that. But you wouldn't want to drink it. The only difference is that extra oxygen. So those are examples of different compounds. There's also like things like table salt. That's another compound, right? It's if you have NaCl, you always have table salt. If it's Na bonded to something else, sodium, this is sodium and chloride, or chlorine atoms bonded together. If sodium was bonded to something else, you have a totally different substance, okay? Okay, I know that's a lot. Let's keep going. Then there's mixtures, right? So remember we had matter, and then we classified matter in 2 different categories. There's either a pure substance or there's a mixture. And then we talked about what constitutes a pure substance, and now we'll talk about mixtures. So mixtures are a type of matter that consists of, 2 or more substances that are physically mixed but not chemically combined. And then consists of 2 or more substances in different proportions. And then consists of substances that can be separated by physical methods. So over here they have a mixture, over here they have a mixture of a liquid and a solid, and you can separate those by filtration. We just did that in lab. We didn't really separate it by filtration in a fancy sense. We just took out our piece of metal, but metal with your water, this would be a mixture, right? You can remove that metal from the water and take it out, and then you'll have your water and your metal. So that's a mixture. All right, and then within mixtures, there are 2 different types of mixtures. So we're looking over at this side. So there's homogeneous mixtures and there's heterogeneous mixtures. And I apologize, I always have trouble saying those 2 words. So homogeneous or homogeneous mixtures, you could think of the Latin root homo as like same. So homogeneous mixtures or homogeneous mixture is a mixture with the composition that is uniform throughout or the same throughout, right? Which means the different parts of the mixture are not visible to the naked eye. So something like brass is actually, you may be familiar with brass instruments. You can't really tell this from looking at it, but that brass is a mixture of copper and zinc. And what kind of mixture? It's a homogeneous mixture, because when you're looking at it, you can't tell that you have those different types of atoms. Okay? All right. And then another homogeneous mixture that I actually like better than this brass example, for various reasons, but this one is scuba breathing mixtures. So in scuba tanks, there's actually a mixture of a lot of different gases, and that's because we don't just need oxygen to breathe, we actually need all kinds of other gases. So nitrogen's a big one. There's actually a lot of nitrogen in the atmosphere. Okay, but there's also some helium in there. So this would be an example of a homogeneous mixture, because if you were to kind of like zoom in on the gas that's in that tank, you wouldn't be able to see the different gases with your naked eye, right? So it would just kind of look like, it would pretty much just look clear. Okay. All right. So that would be a homogeneous mixture. You got a bunch of different types of gases in different proportions, but you can't distinguish between the gases with your naked eye. All right, and then there's heterogeneous mixtures. So looking at this other side of the table now, and heterogeneous mixtures are the opposite, right? You could think of hetero as different, right? So heterogeneous mixtures, the composition varies from one part of the mixture to the other, right? They're different compositions. And then the different parts of the mixture are visible. So the book says water and copper. I actually like to think of pizza. Actually, if you're looking at a piece of pizza, you've got your, maybe your pepperoni, or if you're vegan, maybe vegan meat, fake meat or something. And you can see all those different parts. It's a mixture, but you can see all the different parts, so it would be a heterogeneous mixture, right? You could also think of something like water and oil. So you would see maybe like your oil layer and your water layer, and they're not, you can't mix oil and water, so you would see a difference there, right? Okay, so classification of matter. So this is that infographic I was talking to you about. So you got matter, and then you can break that up into pure substances or mixtures. And then you can break that up even further into elements or compounds for pure substances, or mixtures. You've got homogeneous mixtures and heterogeneous mixtures. Okay, so I actually really like this this graphic here. So if you are lost at any time, it'd be a good idea to kind of take this, look at this and take it step by step. All right, pause the video, do this learning check on your own, and then we'll come back and see how you did. All right, identify each of the following as a pure substance or a mixture. I'm excited, sorry. Just love chemistry. Okay, A, pasta and tomato sauce. What do you think? It's a mixture, right? You can see your pasta and you can see your tomato sauce. If you really wanted to, you could get the tomato sauce off of the pasta. Your pasta might kind of taste a little bit like tomato-y still, but yeah, it's a mixture. There's B, aluminum foil. That's a pure substance, right? It's made of aluminum, which is an element on the periodic table. So that's a pure substance. Helium is another element on the periodic table, so that's also a pure substance. And then air, like we said, is a mixture. It's a mixture of a bunch of different gases. Pause the video, think about it. Is this a homogeneous mixture or a heterogeneous mixture? And then you could try air next. Homogeneous or heterogeneous? All right, next learning check, pause the video, try it out, and then come back. Okay, identify each of the following as homogeneous or heterogeneous. So hot fudge sundae, that's heterogeneous, right? You can see the different types of things in the mixture. It's definitely not just an atom. It's not just an element, right? It's not something like H2O that is always the same in a combined ratio of just your different atoms. It's a bunch of different stuff. So that's a heterogeneous mixture. Shampoo is also a mixture. It's homogeneous though, right? Because you can't see the different, there's tons of different ingredients in shampoo, but you can't see the different ingredients. Sugar water, I want to fight them on this one a little bit just because it depends on what kind of sugar you have, right? Some sugars dissolve really well in water. I mean, if you leave a sugar long enough, it'll usually dissolve in water. But things like, I'm thinking, sugar in the raw. Have you ever tried to put that in your like water or your coffee or like, I don't know if you're drinking sugar water, but in your drink or your coffee, it doesn't really dissolve very well. And so before it dissolves, it would look like it would be a heterogeneous mixture. After it dissolves though, they're right. And it would be homogeneous because you can't see the sugar and the water separated, right? You just see them as a one thing. Okay, peach pie, again, same with the hot fudge sundae. That's a heterogeneous mixture. All right, moving along. States and properties of matter. So, any type of matter that you have can exist, in theory, in different states of matter. So you could think of, solids, liquids, or gases. You could think of water, right? Water can exist as a solid in the form of ice cubes, right? It can be a liquid which is, you know, what we're most familiar with water being. And then it could be water vapor, right? Steam. So whenever people say, would you like any solid water with your, you know, with your drink, you can say yes, because people definitely say things like that. Okay, anyway, so solids, let's start with solids. So solids have a definite shape. Okay, so you could look at this thing over here. That's an amethyst, which is a form of quartz. It contains these different atoms, silicon and oxygen atoms, and they're fixed together in this kind of shape like this. So if you dropped this in water, or you can't really pour a solid, right? It wouldn't be very successful. It's just plop down, right? So it has a definite shape. It also has a definite volume. Okay, so if you put it in a container, it's not going to conform to the shape of that container, right? The volume of that container. It's just kind of itself. It has a definite volume. Particles. It has particles that are fixed together or close together in a fixed arrangement. So a lot of times you'll actually see solids represented like this in a cube, and then you have a bunch of your little, you know, atoms of whatever type of, you know, matter you have. Just kind of like, this is how your particles are kind of stacked up in a solid. And you can see, because they're so closely packed like that, it's so dense, the particles can't really move very much. So they move very slowly. They kind of like vibrate in space there because they want to move, but they like barely can because they're so packed, right? So things to remember, definite shape, definite volume, and particles are close together. And I guess in a fixed arrangement, sorry, you should probably remember that too. All right, liquids. So liquids are a little different. They have an indefinite shape, right? And that just means they're going to conform to the shape of their container. If you put water in a glass, it's going to be the shape of that glass. If you put water on the floor, it's just going to spread out and make a mess. But they do have a definite volume. Okay, so they do take up a definite kind of amount of space. Whereas if it was a gas, you'd have those gas particles kind of like, wee, I'm gonna go out and just fill the entire space. Okay. What else? Okay, so let's highlight those two things. Indefinite shape, definite volume. Okay. And then in liquids, your particles are close together, but they're not quite as close together as solids, and they can move around. So sometimes you'll hear it described like this. They can slide past each other. So that's what gives liquid kind of like the pourability kind of quality, right? Those particles can actually still move. They kind of stay together a little bit, but they can move a lot. Okay, so let's highlight that as well. And they do move slowly. They have a little bit, they move a little faster than solids. Solids move very, very slowly. Liquids move slowly, but not super slow. And then gases, you'll see, move fast. High energy. Okay. All right, gases. Gases have an indefinite shape and an indefinite volume. Okay, so meaning when you put a gas in a balloon, it's going to take the shape of that balloon, just like a liquid might. Okay, or would. And then an indefinite volume is like, instead of like a liquid where that volume is going to kind of stick like this, right? You have, if you try to do the same thing and you put a gas in like a cup, right? Those molecules or those particles are just kind of zoom out of the glass here, like go every which way. That's kind of a weird drawing. So like if you popped this balloon, those gases would just kind of dispense out, right? They just kind of zoom all over. Okay, so they just take the same shape and volume as their container. So if the container is closed, you'll have your gas kind of enclosed in that container, but the second you take the top off of that container, that gas is going to go all over the place. Their particles are far apart and they move really fast. Okay, so they move very fast. They like even just like collide with each other. They're like zooming around and just kind of bumping into each other, and it's chaos. Fun chaos, but chaos. Okay. All right, learning check. Pause the video and then we'll talk about it. Okay, so A, it has definite volume but takes the shape of the container. That's a liquid, right? So we have, you know, your definite volume, right? If we pour that liquid in a glass, it's going to take the shape of the container, but it's going to kind of be a set volume. Particles that move rapidly, that's a gas, right? We just talked about that. Gases have particles that are far apart, so they can move a bunch, okay? As opposed to a solid where those particles are packed in really dense and they can't move very much. Particles fill the entire volume of a container, that's the gas, right? So for instance, like if you have gas in this container and it's closed, right? You've got, they're going to fill up that whole volume, right? They'll get as far apart from each other as they want. Whereas with a liquid, they're going to kind of like sit together like that. Okay. And then, which one were we on? Particles have fixed arrangement. Those are solids, right? Remember, they kind of like pack together like that. And then particles are close together, but they're moving randomly. Close together, but moving randomly. So close together lets you know it's not a gas, right? Those are far apart. But they're moving randomly. That's going to be a liquid, right? Remember, solid particles in a solid don't really move a whole lot. Liquids do. All right, and then we have physical properties. So physical properties are characteristics that can be observed or measured without changing the actual identity of a substance. So this is like shape, physical state. So state, like these that we talked about, solids, liquids, and gases. That's the state that the matter is in. Right, you can have solid water, you can have liquid water. Either way, it's still water. It's just in a different state. Okay, so shape, physical state, boiling and freezing points. So what point does your water boil at? Well, I can boil my water, but it's still water, right? I can freeze my water, but it's still water. Density is actually also a physical property. So remember, density equals mass over volume. Okay, and then color of the substance is just a physical property. It can be observed, it can be measured, but you're not going to change the substance. Likewise, density can be observed and measured. It's not necessarily going to change the substance you have. Physical properties of copper, for example, are its color, so it's reddish and orange in color. It's shiny. It's a great conductor of heat and electricity. That's just a physical property. That's something that we observe about it. It's a good conductor of heat and electricity. So you could think of like copper wire is used in a lot of electrical circuits and stuff like that because it's a great conductor. It's a solid at 25 degrees Celsius. That's not really changing what you have, right? It's just, that's when it's a solid. Has a melting point of 1083 degrees Celsius and a boiling point of 2567. Okay, so boiling points, freezing points, those are all physical properties. So we talk about physical properties, which are like things about the substance, right? And then we talk about physical changes, which are changes that can occur in a substance if there is a change in state. So water, let's say like water freezes or something like that. So liquid going from a liquid to a solid, or a liquid to a gas, and vice versa, right? Or even a solid to a gas, and we'll talk about what that actually looks like. There's also changes in physical shape, right? Trying to think, you can melt copper down and then change the shape of copper, right? And then no change in the identity or composition of the substance is happening during a physical change. You're not changing what the substance is. You're not changing what it's composed of. You're just changing what it looks like, what you observe about it. Okay? So, classify each of the following as a change of state or a change of shape. Change of state, like solid, liquid, gas. Change of shape, you get the idea. All right. Let's see. Chopping a log into kindling. That's just a change of shape, right? It's still a log. It's still in a solid form. It's just changing the shape. Water boiling in a pot, that is a change of state, right? You're boiling the water. So it's going from, remember, when you're boiling something, you're taking the liquid into a gas, right? So you're, oh, sorry, I actually meant to put that, well, I guess we'll keep it, we'll move this up here. I meant to put it there. Okay. Ice cream melting, change of state, right? You're going from, oh my gosh, sorry you guys. I don't know what I pressed. Okay, you're going from a solid, right, to a liquid, which kind of sad. We don't want our ice cream to melt. Ice cream forming in the freezer is the opposite, right? Cutting dough into strips, still dough. We're just cutting the shape of it, changing the shape of it. Sorry, still solid dough, I should say, just changing the shape. All right, that's very different from chemical properties and changes. So chemical properties describe the ability of a substance to change into an entirely new substance, okay? So instead of just changing the state, you're changing from something to a different substance. When a chemical change takes place, the original substance is turned into one or more new substances with new chemical and physical properties. Okay. So for a chemical change, a new substance forms that has a new composition, new chemical properties, and new physical properties. So the book gives the example of sugar caramelizing at high temperature. That's an example of a chemical change. In fact, a lot of cooking is an example of a chemical changes. So flan has a topping of caramelized sugar. When you put that sugar on top of the flan before you cook it, it's actually a completely different, it has completely different composition, chemical properties, physical properties, looks different, tastes different. Then after you've cooked it, after you've added heat and induced a chemical change. Okay? So caramelized sugar is different than sugar. So classify each of the following properties as physical or chemical. Pause the video, try it out. All right, ice melting in the sun. Yeah, it's just physical. Still got water, but it's just melted water. It's liquid water now, okay? Paper burning. Paper burning is actually a chemical change. Yeah, so when you burn paper, we call that a combustion reaction when you burn things. And we'll talk about that in the future, but you don't have paper anymore after you burn it, right? It's completely different. It turns into ash, actually just turns into carbon. Okay, it's no longer paper. A silver knife tarnishes. Yeah, that's actually also a chemical reaction. Okay, it happens when silver is exposed to air or oxygen for a long time, and it tarnishes. It's actually that top layer is actually no longer just silver. Okay, and we'll talk about that in the future as well. A magnet removing iron particles from a mixture. That's physical. You still got iron particles. You still have your magnet. You still have your mixture. You're just separating those things. So that's just a physical change. You haven't changed from iron particles to a different type of particle, right? Okay. I know, and sometimes these can be kind of like, it takes a little bit of time to get good at classifying these things. So let's keep trying. Let's keep working on it. Classify each of the following as physical or chemical changes. All right, burning a candle. Yeah, chemical. So just like burning paper, you don't have the same thing that you start with left over at the end. Okay, you still have matter. You still have that matter. You didn't lose matter, but you're changing what it is. Okay, burning a candle. Ice melting on the street, physical, just like, you know, ice is liquid or solid water, and you're turning it into liquid water. Toasting a marshmallow, chemical, just kind of like that flan that we talked about, the sugar on top, right? Toasting a marshmallow is a chemical change. You are changing that marshmallow chemically. You're changing it. Cutting a pizza, that's just physical, right? You got pizza in the beginning, you just got smaller pizza at the end, smaller size of pizza. Iron rusting in an old car is chemical. Yeah, iron rusting is a chemical change. You're taking iron and you're actually turning it into iron oxide because of the oxygen. Yeah, so you no longer just have iron. And that'll probably make a little bit more sense once we actually talk about some of these chemical reactions. Okay, so I've been talking to you for a while now. I think it's probably time to take a break. So let's go ahead and stop the video for now, and I'll come back and we'll talk about 3.7. Okay.